Okay, L'Hopital's rule. This is how it's spelled. It looks like La Hospital, but there's no S here. It's not hospital. It's pronounced L'Hopital. And it's a way of taking some limits. It's a trick to help us take limits. It does not help us take derivatives. It is not a new version of quotient rule. A lot of mistakes happen there. And we can use L'Hopital's rule when we have these indeterminate forms, 0 over 0 or infinity over infinity. Now, sometimes we can turn these guys into these guys. If we have 0 times infinity, there are ways I could turn that into 0 over 0 or infinity over infinity. Sometimes if I have infinity minus infinity, I can change that into something that looks like one of these and use L'Hopital's, or 0 raised to the infinity or 1 to the infinity. And when I say all these, I always mean as a limit. When I say nothing ever actually equals infinity, we mean if we have limits that are tending to infinity, and we have an indeterminate form of infinity over infinity, L'Hopital's rule will apply. Same with all these guys. When we cannot use L'Hopital's is when we don't have one of these forms. For example, there's no 0 times 0, or 0 raised to the 0, or 1 to the 0. 1 to the 0 is just 1, even in any kind of limit. Infinity times infinity is just infinity in a limit. 0 times 0 is just 0. Okay, so what does L'Hopital's rule say? So it says, if you happen to know a couple of limits, limit as say x approaches a of f of x equals 0, and limit as x approaches a of g of x. So say both of those limits are 0. You already know that. Then the limit as x approaches a of the fraction f over g will equal the same thing as if we take the derivatives of top and bottom. If, and this is a big if, the limit exists. Okay. And you'll see in practice what we do is anytime somebody's asking you to take a limit, first thing you do is just try plugging it in and see what you get. If you get a number, you're done. If you're trying to take a limit and you get 7 as your answer, the answer is 7. You're done. There's no work to do. L'Hopital's rule says if you're trying to take a limit and you get something of one of these indeterminate forms, you get 0 over 0, then L'Hopital says you can take the derivative of the top and bottom. This is a G prime here. Take the derivative of the top and bottom, and that will preserve the limit if that original limit actually does exist. How do we know we're allowed to take this step? Because once we get here, if we get a number, then that limit must have existed, or I was not allowed to do this step. All this will make sense once we see a bunch of examples. L'Hopital's helps us take limits that we might not otherwise know how to take. It is not a new version of quotient rule. It does not help us take derivatives. Okay. So similarly here, I can still use L'Hopital if both the top and bottom limits are infinity. And remember, this is not a true limit. This is an abusive notation saying that a limit equals infinity. Limit's a number. We never actually equal infinity, but we know what this means. That means the function gets bigger and bigger without bound. And same here. So if you've got yourself a fraction and both the top and the bottom are shooting off to either positive or negative infinity, then L'Hopital says you can take the derivative of the top and bottom and try taking that limit again. If you get an answer once you've done that, then that's the answer to that original limit question. This is not a new version of quotient rule. This does not help us take derivatives. It helps us take limits. Okay. Let's do a bunch of examples and this will make more sense. It says example 1. Let's say I want to find the limit as x approaches 0 of 4x squared minus x over x. First, anytime somebody asks you to take a limit, first thing you always do is try plugging it in. So try plugging in x equals 0. See what happens. So I like to say here, goes like, see, I'm going to put a little limit as x approaches 0 of 4x squared minus x over x will go like, that's a little tilde there. What do we get when we plug in 0 on the top? I'll get 4 times 0 squared minus 0 over 0. That goes like 0 over 0. So I have an indeterminate form of the form 0 over 0. L'Hopital's rule applies. I'm allowed to use L'Hopital. Provided I get an answer. Once we use L'Hopital's rule, if we get an answer at the end and I say the limit is 3, then I was allowed to write all these equal signs. If I don't get an answer, then the original limit didn't exist and I wasn't allowed to write all these equal signs. Okay, so here's how this will work. Limit as x approaches 0 of 4x squared minus x over x will equal, and I'm going to write here, I'm going to tell the reader, why am I writing this equals? Because I'm using L'Hopital. And we all mathematicians just kind of do this. We kind of write L apostrophe H here, telling the reader, I'm using L'Hopital here. And what am I going to do? I'm going to take the derivative of the top and bottom. Derivative of the top would be 8x minus 1. Derivative of the bottom is 1. I did not take the derivative of the whole fraction. There's no kind of quotient rule here. I'm taking the derivative of the top by itself over the derivative of the bottom by itself. Now, is that equal sign true? I don't know. I might have lied to you right there by writing that equal sign. Let's try taking the limit again and see what happens. Anytime somebody asks you to take a limit, the first thing you try is just plugging it in. What would I get if I plug in 0? I would get 8 minus 1 over 1. I would get 7. I've taken the limit now. I don't have to write limit anymore. I took the limit. I got an answer. I'm done. The answer is 7. So yes, this equal sign was allowed because the limit existed. So somebody asks you to take a limit, first thing you do is try plugging it in. If you get an answer to begin with, that's your answer. If you get 0 over 0 or infinity over infinity, then L'Hopital's might apply. You take the derivative of the top and the derivative of the bottom, and you try again. If you get an answer, you're done. If you don't, maybe you try L'Hopital's again. Let's try this guy. What if I want the limit as x approaches 0 of 2x over sine of x? Let's check and see what kind of behavior we have. So I'm going to write here, this goes like, I'm looking for my indeterminate form. Plug in a 0 on top, we get 0. 2 times 0 is 0. Sine of 0 is 0. So I have an indeterminate form of type 0 over 0. I'm allowed to try L'Hopital's. Then limit as x approaches 0 of 2x over sine of x will equal, same limit as x approaches 0. This part doesn't change, but now I take the derivative of the top. I'm not using quotient rule here. I'm not trying to take the derivative of the fraction. Derivative of the top is just 2. Derivative of sine, the bottom, is just cosine. Now I try again. How do I justify this equal sign? By writing here, I use L'Hopital, LH. Take this limit. Just by plugging in 0, we get 2 over cosine of 0. Cosine of 0 is 1. I get 2. That means, yeah, this equal sign was true. You never know until you get to the end if you were even allowed to do this. But if you get an answer at the end, you're done. That's your answer. The limit as x approaches 0 of 2x over sine of x is in fact 2. Right, what if we had limit as x approaches 0 again of sine of 5x over sine of 3x. First thing we do, first thing we try, plug it in, see what happens. So this will go like, we'll tilde here, sine of 0 over sine of 0. Sine of 0 is 0. So my indeterminate form is 0 over 0. So I'm allowed to try L'Hopital's. If you don't have 0 over 0 or infinity over infinity, you're not allowed to use L'Hopital. So let's try using L'Hopital now. So this will equal, and again, I'm going to tell everybody I'm using L'Hopital by writing a little L apostrophe H there. Let's take the derivative of the top. The limit as x approaches 0. Derivative of the top will be cosine of 5x times 5. I have to use chain rule there. And the derivative of the bottom will be cosine of 3x times 3. Now let's try again. So you take derivative of the top, derivative of the bottom separately, and then try taking your limit again and see what happens. So on top, I'm going to get cosine of 0, that's 1 times 5. Cosine of 0, again, 1 times 3, I get 5/3. I got a number as my answer. I'm done. That's the limit. So the limit of this fraction as x approaches 0 is 5/3. Okay, let's try another one. Let's say we had the limit as x approaches infinity of x squared over e to the x. Okay, so let's look at our behavior. How does this go? What's this go like? As x is approaching infinity, what happens to x squared? That also goes to infinity. What does e to the x do? Think about the graph of e to the x. Here's e to the x. Here's x squared. Both of them are going to infinity. So I have an indeterminate form of type infinity over infinity. I'm allowed to try L'Hopital's. So limit as x approaches infinity of x squared over e to the x will be, if this limit exists, the same limit when I apply L'Hopital, meaning take the derivative of the top and bottom. What's the derivative of x squared? 2x. What's the derivative of e to the x? E to the x. And now we try again. What happens as x approaches infinity of 2x? That still goes to infinity. What does e to the x do? That still goes to infinity. So I did L'Hopital's, and it looks like nothing happened. Like I still didn't get a number, but I still have an indeterminate form. That's still infinity over infinity. I'm allowed to use L'Hopital's more than once, provided I get an answer at the end, provided I get like just a number at the end. I'm allowed to use L'Hopital's over and over again as long as I have an indeterminate form of either 0 over 0 or infinity over infinity. So we're going to try again. We're going to keep going. So limit as x goes to infinity of 2x over e to the x. If I apply L'Hopital again, the derivative of 2x is just 2. Derivative of e to the x is e to the x. What does this function do as x goes to infinity? So think about this function. The top is not going to infinity. The top is a constant over infinity. Anything that looks like this, where you have just a number over infinity, that limit is 0. So I got an answer. That's the limit. This function approaches 0. It's a horizontal asymptote of this function. I got an answer. That means, yes, I was allowed to use L'Hopital here, and I was allowed to use it there, and that's this guy's limit. Now, I want you to get good enough at these infinity over infinity types that you just look at it and know what answer you're going to get. We want to think dominating behavior. Anytime you've got something that's like infinity over infinity, always remember these. Exponentials beat polynomials, which beat logs. So, like, you're going to do a lot of limiting behavior in Calc 2. Especially when you get to like sequences and series, you're going to look at end behavior of things that look like fractions. And you just got to be quick that you can just look at it and know the answer. Exponentials are always going to beat any kind of polynomial, and any kind of polynomial is going to beat any kind of log. So if an exponential is in the bottom versus a polynomial, if I wanted the limit as x approaches infinity of x to the 100th power plus 1 billion, or however many zeros I'm writing here, over 2 to the x minus 1. Both the top and bottom are trying to shoot off to infinity. This goes like infinity over infinity. The question is, who's getting there faster? Who's dominating? Who's growing quicker? And any exponential will beat any polynomial. Sure, that's to the 100th power, but this guy is growing exponentially faster than that one's growing. Get out your graphing calculator and try doing like maybe 1000 to the 100th power plus all that stuff over 2 to the 1000th power. Try plugging in a big value of x. Oh, that was a 100. The bottom is going to be much bigger than the top. The bottom is going to dominate. Any exponential is going to be any polynomial. So I know just glancing at this, that this limit is going to equal limit of that stuff is going to equal 0. If the bottom wins, the answer is 0. If the top wins, then the limit's infinity or negative infinity. Now I could use L'Hopital's on this, but notice here I had a quadratic and I had to do L'Hopital's twice to get there, because I had to keep taking the derivatives until that x went away and I just got a constant. Because that was a quadratic, I had to do L'Hopital's twice. If I wanted to do this one by hand, I would have to do L'Hopital's 100 times. And nobody's got time for that. This is why I want you to just know what the answer is. Because in Calc 2, you're not going to have time to use L'Hopital's 100 times on this. Let's look at another example. Let's say we had limit as x approaches infinity of 8x cubed minus 2x squared plus 5 over 9x cubed plus 3x squared plus 1,000, 10,000, whatever. Okay, let's look at our end behavior. Let's look at our indeterminate form. The top, that's x cubed, that's going to infinity. The bottom, that's also x cubed. It's going to infinity. So this is an indeterminate form of type infinity over infinity. I'm allowed to use L'Hopital's. So I'm going to write this out in all its gory detail here. The equals, provided I get an answer at the end, using L'Hopital's, I'm going to take the derivative of the top and bottom. So the derivative of the top will be 24x squared minus 4x. The derivative of the bottom will be 27x squared plus 6x. Now, we try again. Thinking about the limit as x goes to infinity. I've got squared. X squared goes to infinity. So this goes like infinity. What about the bottom? X squared still. I still have infinity over infinity. I'm allowed to use L'Hopital's again. So this will equal using L'Hopital's again. Take the derivative of the top, we'll get what? 48x minus 4 over, what is that, 54x plus 6. Let's check our type. As x goes to infinity, the top goes to infinity. As x goes to infinity, the bottom also goes to infinity. We're still in an indeterminate type, indeterminate form of type infinity over infinity. I'm still allowed to keep using L'Hopital's rule. So we get limit as x goes to infinity. Take the derivative of the top. We get 48. Take the derivative of the bottom, 54. There's no x left anymore. That limit of a constant is just that constant. The limit exists. We're done. It's 48 over 54. Okay. Now, that will reduce. 6 goes in here 8 times. 6 goes in here 9 times. That's 8/9. Think back to college algebra. Think back when you were graphing rational functions and you were looking for the equations of horizontal asymptotes. Remember those 3 cases where if the top is bigger, there's no horizontal asymptote. If the bottom's bigger, the answer is 0. And if you have the same degree, top and bottom, then you take the ratio of leading coefficients. We already knew this answer because I've got same degree, top and bottom. We knew we were going to get 8/9. We've literally just proven that, though. We just had to use L'Hopital's 3 times to get there. Okay, let's do another. Let's do the limit as x approaches infinity of natural log of x over x. So let's check our type. What does natural log do as x goes to infinity? His graph looks like this. It shoots up to infinity. And of course, y equals x, the bottom, shoots up to infinity. So this is an indeterminate form of type infinity over infinity. I'm allowed to try to use L'Hopital's. So then that limit, I'm going to write it all out, will equal, again, tell the reader here, I'm using L'Hopital, derivative of the top, the derivative of natural log of x, 1 over x. The derivative of x is 1. So just cleaning up that fraction there, that's the limit as x goes to infinity of 1 over x. Now, here's where mistakes happen. People will keep trying to use L'Hopital's. They'll do it again and go, oh, 0 over 1. You cannot keep using L'Hopital's unless you still have an indeterminate form. This is not an indeterminate form. The top is not going to infinity. The top is just 1. You cannot use L'Hopital's if you don't have 0 over 0 or infinity over infinity. This limit we can just do. I mean, just think about the graph of 1 over x. What happens to my y values as x approaches infinity? This limit is 0. So this is one of those cases where just thinking about dominating behavior will get you that answer. Like, you would still have to show the work, but you should know the answer immediately. Any kind of polynomial, even a line, dominates any kind of log. Exponentials beat polynomials, which beat logs. So the bottom is bigger. If the bottom's bigger, the answer is 0. If the top's bigger, the answer is some kind of infinity. Okay, let's try this one. The limit as x approaches 0. Now I'm going to 0. 3x plus 5 over 4x plus 2. Okay. Here's a common mistake I'll see. People will do this. They'll say equals L'Hopital. I'm going to write all this out. Everything I'm writing right now is wrong. Derivative of the top is 3. Derivative of the bottom is 4. And they'll just say, oh, that's 3/4. That is all wrong. You're only allowed to use L'Hopital if you have an indeterminate form. The first thing you're supposed to try when taking a limit is just plugging in and seeing what happens. So let's try to plug in x equals 0. If I plug in x equals 0, I'm going to write this out. Limit as x goes to 0, 3x plus 5 over 4x plus 2. I'll get 3 times 0 plus 5 over 4 times 0 plus 2. I get 5 over 2. I got an answer. That's not an indeterminate form. I just did the limit. First thing you try is plugging in and seeing what happens. If you get an answer, you're done. That's the answer. Okay, let's try this one. So first thing we want to try is plugging it in, seeing what happens. Plugging in 3. So we're going to put here, this goes like, well, what do we get? 9 minus 9 over 3 minus 3. We get 0 over 0. That doesn't mean we're done. That doesn't mean stop. That means try out L'Hopital's and see if it helps. This is an indeterminate form. I'm going to start writing this down. Indeterminate form of type 0 over 0. So the limit as x approaches 3 of x squared minus 9 over x minus 3 will equal, how do I know this? Because I'm using L'Hopital. Take the derivative of the top and bottom. Don't forget to write your limit at every step until you take the limit. The derivative of the top is 2x. The derivative of the bottom is 1. Again, mistakes happen here where people would just, they get mad. L'Hopital's is fun. So they just keep taking derivatives. Don't keep taking derivatives. You're done. I don't have an indeterminate form anymore. Now I try plugging in 3 again. I get 2 times 3. I get 6. I'm done. There. And I got that by plugging in, not taking another derivative. If you took another derivative, you would get 2 over 1, which is the wrong answer. You can only use L'Hopital's rule when you have an indeterminate form of type 0 over 0 or infinity over infinity. Okay. What if we had, pause here. Okay, what if we had this guy? Limit as x approaches 0, cosine of x minus 1 over x squared. We try plugging in, see what happens. So we write here, always, I want you to write this on any written assignment. You put a little goes like to figure out our form. If we get an answer, we're done, and we just write equals. But let's plug in 0 and see what we get. Cosine of 0 was 1. X squared, 0 squared, of course, is 0. We get 0 over 0. So we have an indeterminate form. So I just write IF, indeterminate form of type 0 over 0. So we can try using L'Hopital's. Maybe it works, maybe it doesn't. It will. It's 1 over x squared, and we write here equals, and then we say, how are we justifying we're using L'Hopital? If we don't get an answer over here, we weren't allowed to do this, but we won't know this until we try. Derivative of cosine is negative sine. Derivative of minus 1 is just 0 over 2x. And we try again. Oh, 0. We're taking the limit as x approaches 0. We try again. Try plugging in zeros. Sine of 0 was 0. 2 times 0 was 0. We still have an indeterminate form of 0 over 0. So L'Hopital says, well, this limit will exist or will equal the limit of the derivatives provided that limit exists. So let's try again. So let's do L'Hopital again. So that will equal limit as x approaches 0. Derivative of negative sine will be negative cosine. Derivative of 2x is 2. Now we try plugging in 0 again. Cosine of 0 is 1. So I get negative 1 over 2. That's not an indeterminate form. That's an answer. When you get a number, you're done. That's my limit. Okay, let's try some crazier problems. All of those we've done so far have been 0 over 0 or infinity over infinity. Let's try one that's 0 times infinity. Now, you can't directly use L'Hopital's on this type, but a lot of times you can change this in to one of these 0 over 0 or infinity over infinity. So let's say we wanted to do the limit as x approaches 0 from above of x times natural log of x. So y equals x goes to 0. This guy wants to go to 0. He goes to 0. Natural log of x, as I approach 0, the limit as x approaches 0 from above of natural log of x is negative infinity. And remember, of course, that's not a real equals. This is an abusive notation to say that, but it tells us that this function, as I approach 0, tends to negative infinity. Now, I don't care about the negative here. I have something where this guy wants to go to 0. This guy wants to go to some version of infinity. The question is, who's going to win? They're fighting each other. One guy's trying to get smaller. The other one's trying to get bigger. Bigger in the sense of like going to negative infinity, and smaller in the sense of getting smaller in absolute value. So who's going to win? Well, what we want to do is change this into, I need to make this a fraction. I need this to look like either 0 or over 0 or infinity over infinity. So what I want to do is flip one of these guys on his head and turn this into a fraction of fractions. So I could say x times ln of x. I could write that as x divided by 1 over ln of x. Or I could write it as ln of x divided by 1 over x. Let's look at both of those. And like we're actually going to do this problem both ways. Well, we're going to start. You'll see that this is the one we want by far. Okay, so let's look at the limit as x approaches 0 from above of natural log of x over 1 over x. So what happens here? What does this guy tend to? As x goes to 0, this guy goes to negative infinity, but I don't care about the negative. This is going to be type infinity over, what does 1 over x do? Think about 1 over x. As x is approaching 0, this guy wants to go to an infinity. He happens to be positive, but I don't care about the pluses and minuses here. Still type infinity over infinity. The other guy, if I wrote this guy here, as x approaches 0, right, we're going to have to do a little thinking here. The top is going to go to 0. 1 over natural log of x. Natural log of x is going to negative infinity. 1 over infinity, that goes to 0. Top and bottom, so this is top. And all of this, when I say bottom, I mean all of that. Both go to 0. So I could rewrite this guy that was 0 times infinity in either form. I could write it as 0 over 0 or infinity over infinity. And then use L'Hopital's. Let's try this guy here because he has an indeterminate form. So I'm going to write this from the beginning. The limit as x approaches 0 from above of x times ln of x would be the same limit, because I haven't done any math yet, of this guy. All I did was wrote x as 1 over x. That's all I've done. That's just algebra. No calculus happened here. That's of type infinity over infinity. This was 0 times infinity, can't use L'Hopital's. This is infinity over infinity, can use L'Hopital's. So this limit, using L'Hopital's, the derivative of natural log of x is 1 over x. The derivative of 1 over x would be negative 1 over x squared. Now, I've seen this happen before. I'm literally almost done. Like, this problem is almost done. But I've seen people do this. Oh, well, if I plug in a 0, I get 1 over 0. That's infinity over infinity. This still looks like a 1 or infinity over infinity. Let's keep using L'Hopital's. It only gets worse. If you tried to use L'Hopital's on this again, you would just make it worse. This is just let's clean this up. Let's do a little keep, change, flip. This is just algebra here. Just algebra. I've got 1 over x times negative x squared over 1. No calculus happened there. I didn't take any derivatives. Just keep, change, flip. That just cleans up to negative x. One of the x's cancels. This limit I can just do. Limit as x goes to 0 of negative x, that's just 0. I'm done. I'm done. I've taken the limit. So, to recap, I started with something that looked like 0 times infinity. I'm going to have to play around a little bit with algebra to write that as a fraction where I get 0 over 0 or infinity over infinity. Either of those would allow me to use L'Hopital. And there are two different ways I could have written that. I chose to leave the natural log alone and make the x a 1 over x. And I'll show you in a minute why I chose to write it like this. Then we use L'Hopital's by taking the derivative of the top and the bottom. We try cleaning up first before we do anything else. Clean up the algebra, and we realize, oh, well, now we can just take the limit. Okay, what if we had done it the other way? What if we said limit as x goes to 0 from above of x times ln of x was x over 1 over ln of x? Because that's still a true statement. I need my limit in here. And now, well, again, we get type. This goes like 0 over 0. But now let's try taking the derivative of top and bottom. The derivative of x is just 1. What's the derivative of 1 over natural log of x? I would have to think of that as ln of x to the negative 1 power and then take his derivative. That would be negative 1 times leave the inside alone to the negative 2 times the derivative of the inside. So the derivative of 1 over ln of x would be 1 over, negative 1 over, ln of x quantity squared times 1 over x. That's so much uglier than what I started with. It's a true statement that this limit equals that limit, because the limit does exist. I know what I'm going to get. But all I did was make it worse. And even if you try to clean this up and you keep applying L'Hopital's, you're going to keep making it worse and worse at every step. When you have these 0 times infinity limits, You want to make sure that you write it as a fraction so that each derivative is getting easier, not harder. Anytime you've got a log in there and you're doing one that looks like this, if you've got a log, put the log on the top. Put the other guy as a fraction 1 over that. So we could do like a similar example here. Limit as x approaches 0 from above of x squared natural log of x. This is of type 0 times infinity. I could say this is the limit as x approaches 0 from above. And I want to write this as a fraction because I have to have either 0 over 0 or infinity over infinity. Leave the log on top and write x squared as 1 over x squared. All I've done there is written this guy as a fraction of a fraction. Then this is type infinity over infinity. And I'll let you work this out on your own. Answer is going to be 0. This guy's easy to take a derivative of, and he gives you a 1 over x. This guy's easy to take a derivative of, and then do a little keep change flip, and you're done. Okay, what about infinity minus infinity? These don't always work, but sometimes when you're taking a limit that looks like this, you're able to rearrange things to get either 0 over 0 or infinity over infinity. So for example, say I want the limit as x approaches 0 of 1 over sine of x minus 1 over x. So as x goes to 0, sine of x goes to 0. 1 over 0 is infinity in the limit. Same thing here. 1 over 0 in the limit goes to infinity. So this is of type infinity minus infinity. I have to have a fraction. So what we're going to try to do here is combine these fractions together and see if we can apply L'Hopital's rule. So I would get a common denominator. I would multiply top and bottom here by x. Multiply top and bottom here by sine. Then I can add my fractions together because now I've got a common denominator. I get x minus sine of x over x times sine of x. Okay, now let's check our type. Now I've got a fraction. If you're going to use L'Hopital's rule, you got to have a fraction. Yeah, otherwise L'Hopital's doesn't apply. You're not allowed to use it if you don't have a fraction. Let's check our type. Plug in 0. I'm going to get 0 minus 0 over 0 times 0. I get type is in an indeterminate form of type 0 over 0. Let's try using L'Hopital's. So that will equal the limit as x approaches infinity, 0. I keep writing infinity. Take the derivative of the top, 1 minus cosine of x. Take the derivative of the bottom. Now I've got to use product rule here. Derivative of the first times the second plus derivative of the second times the first. And now we try again. Try plugging in 0 again. I'm going to get 1 minus 1. Cosine of 0 was 1, which is 0, of course. Sine of 0, 0. 1 times 0 was 0. I get type 0 over 0. That suggests to me, hey, let's try doing L'Hopital's again. Because the top, I can see, you got to kind of look ahead and see what, look, if I take another derivative of the top, this piece is going to disappear. The bottom might get a little bit worse, but the top's going to get a little better. So let's try again by using, again, we always want to say, oh, I didn't write it here. You tell everybody I'm using L'Hopital, and this is the way you say, you write a little LH. Derivative of the top, derivative of negative cosine will be positive sine. Derivative of sine is cosine. And then I have to use product rule here. So derivative of the first, negative sine, times leave the second alone, plus derivative of the second, which is just 1, times leave the second. Okay. Now what do we get when we plug in? Sine of 0 was 0. And at first you're thinking, oh no, I'm going to get 0 over 0 again. But no, I'm not. Watch what happens. Cosine of 0 is 1. Sine, if you get double 0 there, you get 0 times 0, so minus 0. But then I get another plus 1 there. So I get 0 over 2. I get 0. So my final limit is 0 because I did not get 0 over 0. Don't keep taking derivatives forever. At each step you plug in, if you don't have an indeterminate form anymore, you can't go anymore. Okay, what about some tricky ones? Some other indeterminate forms. So 0 to the infinity. One to the 0. 0 times 0. None of these we can't do. Okay, so if I wanted, say, the limit as x approaches infinity of something like this, 1 over x to the x. So the inside is going to 0, but the exponent's going to infinity. So you might look at this and think, oh, I can use L'Hopital's on this. No matter what you do, it's not going to work. L'Hopital's is not going to help you here. Because the limit's just 0. 0 to the infinity. If the bottom's getting smaller and you're taking that to bigger and bigger powers, numbers close to 0, when you square them, get even smaller. Take them to the 100th power, they get even. This limit's just 0. You don't need no L'Hopital's for this. 0 to the infinity is just 0. 0 times 0 is just 0. 1 times 0 is just 0. If I wanted the limit as x approaches 0 of 1 plus 1 over x to the x. 1 over x goes to 0. The inside is going to 1. The exponent's going to 0. So this goes like 1 to the 0 power. This limit's just 1. These we're not going to do anything crazy with. Same with 0 times 0. Same with infinity plus infinity is just infinity. No, the ones that we can't do. So these we can't do. We don't need L'Hopital's. The interesting ones are 0 to the 0 and 1 to the 0, or 1 to the infinity. These are where we're going to get interesting. So let's look at the limit as x approaches 0 of x to the x. So when you take roots of small numbers, they get bigger. Think about, like, if I just plugged in a really small number, say I put 0.01 to the 0.01 power. Any exponent that's less than 1 but bigger than 0 is equivalent to taking a root. This means that's the 100th root of 0.01. That's actually a big number. So the inside is trying to get small, but taking smaller and smaller roots tries to make it big. We've got some kind of competition here. L'Hopital's always applies when you got some kind of competition. One thing's trying to get big while another thing's trying to get small. Who's going to win? Now, there's a trick we got to use on these. Remember, in order to use L'Hopital's, no matter what form I have to turn it into something that looks like, so I need 0 over 0 or infinity over infinity in order to use L'Hopital's rule. So I'm going to have to play some games here. I'm going to call y x raised to the x power. I'm going to take the natural log of both sides. We're going to do something kind of akin to logarithmic differentiation, but it is not. Take the natural log of both sides. So I get natural log of y equals natural log of x to the x. And then I'm allowed to bring that x down to ground level. Now, why did I do this? Because limit as x approaches 0 of y is limit as x approaches 0 of x to the x. I just took the limit of both sides. So if I can figure out what y is doing, I can figure out what natural log of y is doing. Or another way of saying this is I'm allowed to here take the limit of both sides. And the natural log is a continuous function. With continuous functions, you're allowed to pass the limit inside of the function. So this left-hand side will become the natural log of the limit that looks really messy. And I'm just recopying the other side. This is what I want. That's what I'm after right there. So like if I can figure out this limit, the natural log of the thing I want is this answer. I just make both sides powers of e and I'll be done. Okay, so what we want to work with now is this thing. So let's call this L here. So L equals limit as x approaches 0 of x times natural log of x. So what this line here says is the natural log of the thing I want equals L. I just make both sides powers of e. That means the thing I want will be e to the L. So once I find this limit, I'm almost done. What we just did this limit. This is of the form. This is type 0 times infinity. We just did this. Limit as x approaches 0 of x times ln of x will be limit as x approaches 0 of natural log over 1 over x. And then use L'Hopital. This would be limit as x approaches 0, 1 over x over negative 1 over x squared. And then we did all our cleanup there. That's limit as x approaches 0 of negative x, because one of the x's canceled, and that's just 0. Okay, so just to recap, we're not done. That's not the answer. We wanted this. That's what we want. I called that thing y, and we took the natural log of both sides. So I'm after y. Right now I have the limit of the natural log of y equals, we did that limit on the other side, 0. I'm not after natural log of y, I want y. So we make both sides powers of e raised to the natural log. Those just cancel out, and we just get y equals e to the 0, which is just 1. So the limit as x approaches 0 of x to the x is 1. So who's going to win here? The inside or the outside? Nobody wins. They cancel out. Okay, let's try another one. We'll do a few of these. What if I want the limit as x approaches 0? No, x approaches infinity of 1 plus 3 over x raised to the 4x. So let's check our type here. When x gets really big, 3 over x goes to 0. The inside goes to 1. But the exponent goes to infinity. So this is type 1 raised to the infinity. So the inside wants to be, just go to 1. 1 to any power is 1, right? Like what's 1 to the 7th power? 1. So the inside says the answer should be 1. But the exponent says, wait a minute, everything that's in here right now, sure, this might be getting closer to 1, but every number here is a little bit bigger than 1. Imagine, type this in your calculator. Try 1.001, a really small number, bigger than 1, to the 1/1,000,000th power. Your calculator will probably give you an overflow because this number is so big. Like this is humongous. It's a giant number. So we've got this competition. The inside wants to go to 1. The outside wants to make the whole thing giant. Who's going to win, the inside or the outside? You'll see that it's a balance. Nobody wins. So we call the whole thing y. We say y equals any of these 1 to the infinity or this type here, 0 to the 0. Yeah. 0 to the 0 or 1 to the infinity. We play this game here. Call the thing you're after y and take the natural log of both sides. The entire purpose of taking log is to bring this thing down to ground level. Now, what we really want is the limit here as x goes to infinity of natural log of y. That will be limit as x goes to infinity of this stuff. Let's check our type here. I've got two functions. That guy there, as x goes to infinity, 4x tries to go to infinity. So this goes like infinity. As x goes to infinity, 3 over x gets smaller and smaller, goes to 0. We get natural log of 1. Natural log of 1 is 0. We get type infinity times 0. So we started with type 1 to the infinity. That's a key that you're going to have to take logs of both sides and turn it into something like this. Now I've got infinity times 0. All of these, every time you have infinity times 0, you got to write it as a fraction. Or you take one of your guys and write it as 1 over that. So this thing here, I'm just going to call L, because I'm tired of writing all this. I'm going to assume this limit exists and call it L. So L. All right, so let's just work on this for now. Limit as x goes to infinity of, I want to write this as a fraction. Always leave the log alone. Don't put the log in the bottom. Make this 1 over 4x, or in the bottom 1 over 4x. Convince yourself that this thing right here is the same as this. Okay. Now we're going to have to do a little arithmetic here. We're going to have to do some calculus, but this will work out. Okay. And our type here, we could check our type. X goes to infinity, this fraction goes to 0, 1 plus 0 is 0, natural log of 0, natural log of 1 is 0. Goes like, as x goes to infinity, 1 over infinity goes to 0. This is type 0 over 0, I'm allowed to use L'Hopital. So equals, by L'Hopital, the derivative of natural log of anything is 1 over that thing times the derivative of what's inside. So now I need the derivative of this guy. Derivative of 1 is just 0. Derivative of 3 over x is negative 3 over x squared. Over the derivative of 1 over 4x, and again, you can check this on your own, will be, let's see, we'll have negative 1 over 4x squared. And we're still taking here limit as x goes to infinity. All right, now we're going to clean this up. We don't want to just keep taking derivatives because this is only going to get worse. Clean it up. So like here, we could multiply through by this x squared, or I could just multiply top and bottom by x squared. Here, so I'm just doing algebra. So if I multiply top and bottom by x squared over 1, that'll cancel out this x squared. That'll cancel out this x squared. I'm going to get limit as x approaches infinity of negative 3 over 1 plus 3 over x all over negative 1/4. Okay, again, let's do a little keep, change, flip. So that'd be negative 3 over 1 plus 3 over x times negative 4 over 1. Which I think will be 12 over 1 plus 3 over x. And I need my limit here. I forgot to write my limit. Got to write the limit until we take it. All right, now we can take this limit. This guy right here, there's my only x. I do not have an indeterminate form anymore. The top is a constant. No more L'Hopitals. Top is a constant. I can just take the limit. 3 over x goes to 0. I just get 12. That's not my answer. That's this thing I called L. So what we have here was natural log of y equals 12, because I've taken the limit now. That wasn't y, that was natural log of y. Make both sides powers of e, and you get y equals e to the 12th. That's the limit. Now, this may look familiar to you. You may recall that by definition, e, the number e, is defined to be the limit as n approaches infinity, or x, we can call it x here, 1 plus 1 over x to the x power. That's the definition of E. So if I were to say E squared, all that is this thing squared. That would just be the limit as x goes to infinity of 1 plus 1 over x to the 2x. Because all I did was took this thing and squared it. How do you raise a power to a power? You multiply. And it turns out that if you change this number as well, you change the exponent. So look what we started with. So I've got a 3 there and a 4 there. What ended up happening was they just multiplied and we got e to the 12th. Okay, I've done a whole bunch of examples. This video actually went a little longer than I thought it would. You just got to practice these. Just get in there, practice, look in the book for more examples.